Alright, tonight what we're going to be talking about are how particles exist in the real world as opposed to on paper. If I were to draw a particular compound such as methane, C, which is CH4, okay, so we're going to have C bonded to 4 different hydrogens. The most that I can try to separate them is by 90 degrees, okay, and everything would be 90, and that's because on a flat 2D world, you can only have a total of 360 degrees. But in reality, what these guys want to do is they want to separate as much as possible, and they can actually have more than the 90-degree angle split by existing in the three-dimensional world that they actually do. And what happens is instead, we have these carbon bonded to the hydrogen, and they're going to take on a more tetrahedral type of shape, which I always think looks like a tripod where you have the camera on top and then you've got the 3 legs. And what happens is if I actually measured this angle would be 109 degrees versus the 90 degrees. Okay, so which one it takes up or has a bigger angle? Well, that would obviously be the 109. And so it's going to want to prefer this type of a shape where it's tetrahedral as opposed to this one where it's only in the 2-dimensional world. Now, why is that, you ask? Well, and that comes along because of something called the VSEPR theory. And VSEPR is V-S-E-P-R. And what VSEPR stands for is valence, shell, electron, pair, repulsion. So that's valence, shell, electron, pair, repulsion. And what that actually tells you is that electrons, they like to repel each other. Why? Because electrons are negative and they do not want to be by other negatives. So what they're going to do is they're going to try to take a shape where those electrons or the electrons that are involved in these bonds are as separate from one another as possible. Okay, so they're going to try to exist in a world where they have as much space or separating them from their other electrons as possible. What we're going to do now is try to identify how these different shapes are. Okay, so we've got Br2 as our first example. So I've got 2 Brs. Normally it tells you to choose a central atom. In this case, there is no central atom. So you're just going to kind of look for on the chart to the left about what it would be. And that would be 2 atoms adjacent to each other. Well, what's the only shape two things can make? Well, that would be a line. So this would be linear. It doesn't, sometimes it has 0 lone pairs, sometimes it has up to 3. So that's why it'll change. It'll be between 0 and typically 3 lone pairs. The bond angle for any line would be 180, and this is what my sketch would actually look like. Alright, so this would be a linear structure. Okay, my next one I'm going to want to do is CO2. So what I'm going to do is I actually have a central particle, and that would be the carbon. The carbon is directly attached to 2 different substances, and you also need to look at the lone pairs that are located on that carbon, and this carbon has 0 lone pairs. So what I'd be looking for is a center atom that's attached to 2 atoms. Well, here's one and here's one, and I see none others that are attached to 2 atoms. But what I'm also looking for is how many lone pairs does it have. This guy says 0, this guy says 2. So I would be looking at the one that is attached to 2 with 0 lone pairs, so this would take on a linear shape. So this too would be a linear shape. Okay, now we're going to do NH3. So once again, you're going to see how many things is the N attached to. That would be 1, 2, 3. So I'm looking for something that's attached to 3. So here's one and here's one. So the difference between these 2 different shapes is that one has 0 lone pairs, one has 1. And I look at my nitrogen and it has that 1 lone pair right there. So it would be the trigonal pyramidal shape. So I'd write trigonal pyramidal or pyramidal, depending on who the teacher is, who they learn by, how they talk normally. Okay. All right, then we're going to look at that CH4. CH4 is the center atom is attached to 1, 2, 3, 4. So I'm looking for something that's surrounded by 4 atoms. As of right now, that's my only option. So hopefully the rest of it will fall into suit. And then it has 0 lone pairs according to this. Well, that guy has 0 lone pairs, so we're good to go. So this would take on a tetrahedral shape, which is exactly how I thought the tripod would look. Alright, now what we're going to be doing is we are going to be looking at water. Water is attached to two different particles. So once again, we're dealing with the center atom surrounded by two atoms with how many lone pairs? So that would be 1, 2 lone pairs. So this would take on a bent shape. Now if you notice, it's drawn as if it was linear, but what it actually exists at, because of the lone pairs, it would exist in a bent shape. Okay, more of like this type of a look. Right, now we're going to look at HCO3, looking at my drawing for H2CO3, or H2CO, I'm sorry. So H2CO, what we're going to do is it's attached to 1, 2, 3 different things. So that would be 1, 2, those two guys. I'm going to erase this so you guys don't get confused. And how many lone pairs does that center atom have? Well, it has 0. So this would be a trigonal planar shape. All right. Now what I wanted to talk to you is a little bit about these bond angles. And if you notice, between the bent, the trigonal pyramidal, and the tetrahedral all have 4 kind of things attached to them. 1, 2, 3, 4. 1, 2, 3, 4. And if I got rid of this, okay, and we looked at that guy, this would have 1, 2, 3, 4. But what you should notice is that even though their angles are very similar, only ranging between 105 and 109, they do get smaller and smaller as you add more lone pairs. So it goes from 0 to 1 to 2. My bond angle actually gets tighter to go from to 109 to 107 to 105. Well, why does it do that? Well, the whole reason why is because of how much space a lone pair takes up compared to a bond. When you have a bond, such as between a carbon and a hydrogen, they are sharing those 2 electrons, okay? So sometimes those electrons are on the carbon, sometimes they're on the hydrogen, they're moving back and forth. Whereas opposed to if you look at a lone pair, such as the ones on oxygen for water, those lone pairs are 100% of the time spent on that oxygen. So therefore they are going to take up more space. You could kind of think of they have two electrons that are trying to take up the space as opposed to the 1 electron that's being shared between these bonds. So as you add more lone pairs, your bond angles between the elements actually get tighter and tighter. All right, I hope you have a full understanding of bond shapes and can be able to identify while using the chart. Have a great night.